Back in February, astronomers announced that they'd seen the cosmic dawn, the moment where the first stars form and light flooded the universe. And that remarkable discovery was down to this small instrument here in a remote corner of Western Australia. So how did they do it? And what else can the extraordinary telescopes here tell us about the universe? Welcome to the sky at night in the Outback. And we're here at a surprisingly busy airfield in Perth, Western Australia, because we're heading to the Murchison Radio Astronomy Observatory. It's nearly 1,000 kilometres north of here, so that would be a 13-hour drive on untarmacked roads. So this feels like the better option. With the kit and the crew on board, we're all set and ready to go. Started our descent down towards the site. You can see how remote it really is. In an area the size of a small European country, only about 100 people live here. That's why, apart from the occasional scientist and engineer, no one gets to visit. The Murchison Radio Astronomy Observatory is one of the most famous astronomical sites anywhere on the planet. It's dedicated to one particular type of telescope: radio telescopes. They detect wavelengths of light beyond the visible spectrum. And since the 1950s, radio astronomy has transformed the way that we see the universe, revealing exotic phenomena like pulsars, quasars, and evidence for the Big Bang.
For visiting our country before we start, just a bit about Wadgery, I suppose. History shows that Indigenous Australia has been around for somewhere in excess of 60 to 65,000 years now. Late 1800s, the explorers started to move into the Murchison. So enjoy your trip here today, enjoy your travels, and welcome.
Thank you. It's amazing to think that people have lived in this vast, remote, open space for millennia. But it's that very isolation that makes it so ideal for radio astronomy. I met with Lisa Harvey-Smith to get an overview of the site. Well, it's an amazing place. It's not quite what I expected. It's greener than I expected for a desert. But tell me about the landscape and the land that we're standing in.
This is the land of the Wadjuri people. They're traditional owners of this land, and we're very grateful to be here, and we collaborate with the Wadjuri people on the telescopes. In fact, they named all of our antennas in their language, so we have a great connection with them. It can be inhospitable. In the temperatures in the 40s during the summer, so it's a very difficult place to work and certainly to live. That's why not many people live here, as well as the radio quietness aspect.
So what do you mean by radio quiet?
Well, radio quietness is almost like similar thing to getting away from light pollution. So radio waves are emitted by galaxies far away in the universe, by our sun, by the galaxy that we live in. They're also emitted by computers, by mobile phones, all that stuff that we use in our modern technology. So we really want to get away from towns, cities, and even 100 miles from somewhere like a town is too close.
So just how faint are the signals that we're looking for?
Well, we are looking for signals that have travelled through space for about 13 billion years. So you can't really imagine how faint that is. But essentially, towns and cities are screaming at us in radio waves. If you put one single mobile phone on Pluto, we would be able to detect it as a very bright signal with these telescopes. So we just need to be right away from those kinds of things.
So as an astronomer, you wouldn't normally come up here?
That's right. We do remote operations. So I myself normally do my science sitting in an office in Sydney. So we have, of course, internet connection, which can control the telescopes from wherever we are in the world.
Being miles from modern infrastructure is what makes this site so special. But there's also a downside. Now, this is a very remote site. That's why you're here. What are the engineering challenges of building high-tech instruments here?
Well, there's no grid power here. There's no running water until recently. So, you know, it's a very difficult place to live and work. The heat, the remoteness makes it difficult. We've actually had to build an entire power station on site here with 50% renewable energy.
That's solar power.
Of
Yeah,
course.
yeah,
Look,
yeah.
we've got beautiful sun here. We've got a huge computer here, and we have to have that on site because it needs to be close to the telescopes, but we also need to shield it because we don't want the radio waves that computers generate going out into the telescopes again and interfering
Otherwise, you
with the
detect
signals.
yourself.
We would. All we'd hear is this giant scream from the computer, and rather than seeing galaxies. So what we've done, we've created a huge screen of metal around the computers, which doesn't allow the radio waves through. So we go to great lengths.
You really have thought of everything.
Pretty much.
Apart from us.
Fingers
So
crossed.
we're OK here
Well,
with the cameras?
Yeah, so we generally don't allow cameras on site or electronic equipment. We're not currently observing, and we've gone to special lengths today to allow you to film here. But normally,
OK.
nobody's here and nobody's filming.
Well, thank you very much. We'll make the best of it. Lisa, thanks. We'll catch up with you later.
Great. Thanks, Chris.
Radio telescopes are used to study many aspects of our universe, from our own sun to distant stars and galaxies, and even the cosmic microwave background radiation that's left over from the Big Bang. But one radio telescope based here is looking back to the early universe for one very crucial moment. The moment stars first formed, the cosmic dawn. Pinpointing when this moment happened has been one of the great mysteries of astronomy.
Back in February, this site suddenly became the centre of the astronomical world when a team based here announced that they discovered the cosmic dawn, the moment when the first stars lit up the universe. And believe it or not, they did it using this.
This unassuming metal table is called the Experiment to Detect the Global Epoch of Reionization Signature, also known as EDGES. I met with Anthony Schinkel to tell me what it is, what it's found, and what that might mean.
So we're standing pretty much on edges, and it doesn't look like anything I've ever seen before. What are we looking at?
It's an amazing antenna. So this incredibly simple device is literally just a single dipole antenna. So it's very similar to the kind of old-fashioned TV antennas that the older ones of us will remember from the 60s and 70s. But it's taken to a really high level in terms of stability.
So it's controllable so that nothing changes over a long period of time. And that's because it's looking for a very faint signal.
That's right. So the whole problem with this frequency range, down around 100 megahertz and below, is it's so dominated by man-made radio interference, by our FM radios, our TV stations, all of that. So that's why we're out here at the Murchison Radio Astronomy Observatory for a start. But also, even here, we do get a little bit of those signals leaking through.
Low-frequency signals travel a long distance,
They travel
after all.
huge distances, that's right. And so the other thing you have to make sure is that your instrument is very, very stable.
What exactly is it looking for?
So what EDGES is after is a dip in the spectrum of the CMB, the cosmic microwave background.
So that's the first light in the universe.
Exactly. The CMB comes from after the Big Bang, and that dip in the CMB spectrum is what EDGES was after and it appears to have detected.
And if that detection's real, then we can say something about when the first stars appeared.
Exactly. That tells us exactly the epoch that this occurred at. And so it's about 180 million years. So that indicates then, it's an indication that the first stars were around 180 million years after the Big Bang.
That's really soon.
It's really soon. So the earliest stars seen before, I think by Hubble, have been around 400 million years after the Big Bang. And so this...
And that's when we start to see their light.
Exactly.
Yeah,
So this is possibly the first evidence that stars were there at about half that age, because it is a very exciting result and a very new result.
The signal detected by EDGES tells us about the appearance of the first stars. The moment when the hydrogen gas that filled the early universe clumped together until, at a few critical points, it became so dense that fusion occurred and the first stars burst into life. The cosmic dawn.
It's amazing to me that something that looks this simple, even if it's very carefully designed, can tell us about the first stars being so early.
It really is. It's an incredibly exciting result. And I think it's a wonderful example of two things. A very carefully thought out, simple experiment that they've spent a lot of time calibrating and designing, and combined with a great site. Because this frequency band in particular, you simply couldn't have done this work at many other sites on the planet. You have to get away from all the man-made radio background.
So the message from EDGES is that the first stars existed and were affecting their surroundings when the universe was just 1% of its current age, 180 million years. That's much earlier than anyone would have expected, and the signal it detected was much stronger than people thought too. And this throws up a real conundrum. How do we explain this signal? The team here have already built new experiments, like the one behind me, to try and follow up on the EDGES discovery. But we still need to explain this mysterious signal. And the truth is, we don't really know how to do that, although astronomers have published more than 40 papers already with different explanations. Some say you could modify gravity to explain the strength of the signal. Others think that dark matter has got something to do with it, the mysterious substance that we think makes up most of the matter in the universe. Others think it's just a quirk of the electronics, not real at all, or maybe interference from our own Milky Way. It's certain to exercise the minds of astronomers for years to come. But with new experiments to follow up on EDGES on the way, hopefully we'll get an answer soon. Radio telescopes let us see some of the most distant objects in the universe, and that means they look a long way back in time, almost as far back as the Big Bang itself, 13.8 billion years ago. There are several amazing telescopes at this site. One of the oddest is the Murchison Wide Field Array, or MWA. It looks more like an alien invasion of metallic spiders than a telescope. I spoke to Stephen Tingay to find out what it's for. What's the scale of the telescope? We can see it around us here, but how many antennae are there?
Well, we're standing in the middle of the array. So the array consists of 256 of these things, what we call tiles, spread out over a 6-kilometre diameter area. Each tile is a 4x4 grid, so 16 individual antennas. So these are very simple antennas. They just sit flat on the ground. And these antennas can see the whole sky almost all the time, so very simple to operate. By combining all the signals from the individual tiles, we effectively produce a telescope that has a 6-kilometre diameter lens, if you like.
What exactly is it looking for?
The headline science case for the MWA is to look back in time 12 billion years into the first billion years of the history of the universe.
So if you could paint a picture for us, what's the universe like back then?
Imagine a universe with the very first stars and galaxies starting to form out of hydrogen gas, and a lot of this hydrogen gas hanging around, pervading the universe.
The early universe was a strange place. When the first stars and galaxies formed, the space surrounding them was filled with opaque hydrogen gas, which absorbed their light. So even though the stars were emitting light, their brightness was hidden, and the universe remained dark. So when did these dark ages end? And what enabled the light from the stars to finally travel through space?
Those stars and galaxies produced a lot of radiation. And as that radiation was emitted, the hydrogen gas hanging around was split apart. So the electrons and the protons were split apart by the radiation.
And that's this ionisation.
That's the ionisation process. And it's the evolution of that process, the disappearance of this hydrogen gas from the universe, that the MWA is trying to tune into.
This ionisation marked a turning point in the early history of the universe. Gradually, radiation from these early stars spread outwards and split the hydrogen gas molecules, allowing light to seep through, bringing an end to the cosmic dark ages. And it's the signature of that process that you want to try and find with this telescope. How does that work?
Well, the hydrogen gas produces radio emission at a very specific frequency, and so we tune this radio telescope into the frequency of that radio emission in the early universe. So We're looking for the hydrogen gas. When the ionisation takes place, we can no longer see it.
And how long does that process take? Do we have any idea?
Well, we think it takes around about a billion or a bit over a billion years, but I mean, that's one of the fundamental questions that we're trying to directly answer by observing it. There are many, many models for how this proceeds, but what we need to do is test those models with real data. So what we're really doing is trying to set the initial conditions for the evolution that brought stars and galaxies and planetary systems into existence that eventually ended up with us. So it's those initial conditions that we're trying to probe.
So why is the experiment so challenging? Why it takes so many years and so much effort?
We're looking for a signal that originated 12 billion years ago and has taken effectively the age of the universe to get here. It is intrinsically a very, very weak signal, and it has to pass through all the other stuff in the universe. So you've got to extract all the other galaxies from our data to uncover what is this incredibly weak signal in the background. One of the benefits of having to deal with the galaxy and all the other galaxies in order to get to this early universe signal is that you learn all about the rest of the universe, not quite for free, but as a consequence of having to do this really tough experiment. So we've catalogued hundreds of thousands of other galaxies in the universe at radio wavelengths. We're looking at our galaxy in which we live, the Milky Way. So we're looking at the gas and the magnetic fields in our galaxy. We're looking at the products of exploded stars, supernova remnants, and the neutron stars that they leave behind in the form of pulsars.
The sensitivity and range of the MWA also makes it perfect for one of my favourite subjects, the search for extraterrestrial intelligence, or SETI. And I've also seen you've done some work on SETI, looking for alien signals out there. Is the MWA a good choice for that?
I'm quite interested in SETI as a field, and if you want to look for radio SETI, you need to be away from all manner of human-made radio signals because it's very easy to get confused. So here in the Murchison, it's a pristine radio environment. So that means that it's a perfect place to search for radio signals from SETI. So we've looked at other planetary systems, we've looked at asteroid visitors from other solar systems that have passed through our solar system.
That came through not so long ago.
Exactly. So we took the opportunity to look at that with the MWA and put some really strict limits on the existence of radio signals from those objects.
You didn't find anything?
We did not find anything.
It's important to ask that.
Absolutely. And I guess the expectation is that this would be quite rare to find a SETI signal. And one of the benefits of the MWA is that it's a very efficient telescope. You can look at huge parts of the sky very quickly and repeatedly. So as a tool for SETI, it is very efficient.
As well as looking back to the very beginnings of our universe, these radio telescopes are also shedding new light on more familiar objects in our skies. Before we came to the Outback, I met Natasha Hurley-Walker in Perth to learn about how she's been using data from Murchison to explore our Milky Way and other galaxies. Hiya.
Hiya.
This looks amazing.
Thank you.
What exactly do we have behind us here?
So this is GLEAM, the Galactic and Extragalactic All-Sky MWA Survey. Astronomers just love acronyms. We observe the entire southern sky in radio colour. So we use that full bandwidth of the MWA and looked across the entire universe.
What's immediately striking about this data is how colourful it is. I'm not used to that. What does it mean to have colour in the radio?
So what I did when I made the images is I've sort of shifted everything so humans can see it. And it's really important to observe this because the physics of the objects really changes the spectrum at these frequencies. If an astronomer sees a red object in this sky, they know that it's an old and dying object where the electrons that cause the emission are beginning to fade and become very low energy. If they see a blue object, they know that it's very high energy.
Well, should we go on a bit of a tour then? What's this big thing for starters?
Right, OK, so this is actually a distant galaxy. This is Centaurus A. So in the middle of that huge object is just a galaxy, a bit like our own or Andromeda. to human eyes and in the optical, it just doesn't look that interesting. However, when you look in the radio, you can see these tremendous plumes of emission.
So the galaxy's buried in the middle here.
Exactly. The galaxy is so far in there, it's only a pixel on this screen. Right at the heart of Centaurus is a supermassive black hole. And the accretion disk around that supermassive black hole is causing these huge jets to come out. So an object only about the size of our solar system...
That's the black hole itself.
Yes, is causing these jets, which are millions and millions of light years across.
So this is covering, what, a good few square degrees? You could fit the full moon in there a few times.
That's right. It is just a bit bigger than the full moon.
Blimey.
So if you could see in the radio, it would be by far the most impressive thing in the sky.
And what about these backgrounds? I guess they look like stars here. What are they?
Ah, well, a lot of people think they're stars, but actually... every single one of those is a radio galaxy, just like Centaurus itself. So every single little dot is a supermassive black hole, millions of times larger than our own sun, pumping out enormous plumes of radio jets into the interstellar space.
I guess this stripe here is what, the galaxy?
Yeah, this is our own Milky Way galaxy, and there's this long-standing mystery that astronomers have been interested in. Why is there all of this diffuse glow? And the answer, we think, is from supernova remnants, and this is the remains of exploded stars. Astronomers have not been able to detect all the supernova remnants in the galactic plane that they expect to see. So the hypothesis is that we simply can't see them with the current instruments. So we're looking for new supernova remnants, and I have actually found about 30 using this new data.
That's quite a lot, right? We don't think these things happen very often.
That's right, and what's interesting with the radio is you're seeing the kind of the fossilised remains of all of the supernovae that have ever happened in our galaxy. Now, if I just move the image, I can show you some really beautiful regions where we found a tremendous number of supernova remnants. The little soap bubbles.
Oh, these things?
That's exactly right. So everything that's round and circular tends to be a supernova remnant.
Huh.
And this is one of the most impressive examples. This is the Vela supernova remnant, and right in the middle of that is a pulsar. So the MWA is picking up both the fine details of all of these lovely arches of radio emission, but also this beautiful diffuse glow. So it's a really, really huge data set. There's so much to do.
Well, it's a big sky to look at, and it's beautiful as well.
Thank you.
So thank you very much for showing it
Thanks,
to us.
Chris.
Thanks.
Cheers.
For all the discoveries that they've made, the telescopes here have just made the radio sky seem more exciting and more mysterious. And to explore further, astronomers are planning an insanely ambitious new project, and these telescopes are showing them the way. This is the Australian Square Kilometre Array Pathfinder, or ASCAP for short. Its new technology will allow us to peer into the early universe in even more detail. From up here, you get a real sense of the scale of the telescope. The ASCAP dishes stretch almost to the horizon, and it's only by combining them all that you get a telescope with the sensitivity and resolution that's needed to see what they're looking for out in the universe. Astronomers hope that the next generation of telescopes will reveal millions of new radio sources. And that will help us understand more about how the first stars and galaxies formed. With my feet back on terra firma, Lisa Harvey-Smith, one of the lead researchers on ASCAP, explained how it's going to work. So Lisa, we're here amongst the dishes of ASCAP. What makes this telescope special?
Well, as you can see, we've got loads of dishes, in fact 36 of them, spread right across 6 kilometres of the desert. So we use them as a team, and they all look at the same object in the sky at once, and that synthesises virtual telescope the size of 6 kilometres across.
So you get the sensitivity, the resolution of a very big telescope with only 36 dishes.
That's right. It's a lot cheaper and easier that way.
But the real magic for ASCAP's in each individual dish.
Yeah, that's it. It's got such a great technology. In the centre of the dish, the radio waves are focused almost like a mirror in a regular telescope onto what we call a radio camera. So we've created this multi-pixel radio camera, and what it does, it allows our telescopes to have a huge wide-angle view of the sky, so it's kind of like a fisheye view.
A lot of the excitement around this site and around radio astronomy is because of where we're going. Astronomers are planning something called the Square Kilometre Array, or SKA. Can you tell us what that project's all about?
Well, it's a global international project, so many countries are involved, and we're trying to build the world's most powerful telescope. We want to understand the entire history and evolution of our universe. It's just a small question, Chris.
A nice small goal, but it can do the early universe and everything to the present day.
That's right. So it will be sited in Australia right here and in South Africa too. And South Africa will have around 250 large dishes like this. And here in Australia we'll have around 130,000 dipole antennas. So this whole area, up to 100 kilometres across, will be covered in these dipole antennas.
These are things a bit like the MWA antennas.
That's it, a bit taller though. And we call them Christmas trees because they've got that kind of shape. So this whole area will be a cutting-edge observatory to understand billions of years of cosmic history. It's so exciting.
So why do you need something on that scale?
Well, the signals from the early universe are incredibly, incredibly faint. The universe is unimaginably big, and those signals have travelled for billions of years. So we need something this big and this sensitive to really tell us a lot more about what's out there.
It's really hard to imagine this landscape covered in telescope.
It's beautiful. I've seen it from 10 years ago when the very first dish came up and watched them spring up from the desert like beautiful mushrooms. And now we are in the spring and this is all happening again. We're going to build more telescopes and just figure out where we are, what our place is in this wonderful universe.
I'm really excited to see these things here. This is a new design of antenna designed to be part of the Square Kilometre Array, the next generation telescope. So you have to imagine thousands and thousands and thousands of these things stretching as far as the eye can see. It's going to be spectacular. Making discoveries out at the extreme edges of our knowledge demands extreme instruments, and it seems, extreme locations. Here at Murchison, they have both, allowing us to see the universe from its beginning right up to the present day. We came here to this remarkable, beautiful place to find out how the universe got going. And though the results are already incredible, I've got a feeling that the radio astronomers of Murchison are just getting started. Good night.
And The Sky at Night, How to Read the Solar System, A Guide to the Stars and Planets is available now from BBC Worldwide. And hear Brian Cox and Robin Ince on Radio 4's The Infinite Monkey Cage on Wednesday at 9, celebrating the 100th episode of the hit science comedy show.